Hello, my name is Susan Kennedy. I'm here from IntelliSense.io. We are an industrial AI company focusing on the mining sector with a mission to make mining operations efficient, sustainable, and safe through trusted and transparent AI solutions. We optimize every step of the mining value chain. Today, I'm here to talk about stabilizing mine production with end-to-end material tracking. Within your mine, high-resolution visibility of your material means predictable and stable material input into your plant. In your plant, the foresight into the incoming material allows optimization of the plant controls and decisions. End-to-end material tracking breaks down silos between different disciplines and data on site and aids the realization of value of mining operations. On your screen, you can see our Intelligent Mine Experience Center, which we have developed with our partners BSF, which is, as you can probably make out, a digital mine. Now, we're here to talk about end-to-end material tracking. So the obvious place to start this story is in the resource model underneath the pit. Within your resource model, you have information on your material properties and where these are spatially located. Once you blast, you may have a model of how this material is expected to have spread. And from there, you'll go to either your plant or a stockpile. So in this case, I've got an open cut mine and I've got trucks that are hauling the material up to a jaw crusher here and onto a conveyor belt into the remainder of the plant. But it's actually the stockpiles that I want to talk more carefully about. So if we're not going straight to the plant, then we're probably going to a stockpile. And this is where a lot of information is traditionally lost or heavily diluted. So I'm going to talk to you about the hurdles of material tracking in traditional stockpile management and how we have overcome this with a spatially aware model. I'll take you through a tour of the model and how it integrates with other software. And then I'll take you into IntelliSense's platform Brains app, where I'll talk further about the value. After we talk about stockpiles, we'll go into the plant to talk about the value of more stable and predictable material information within the plant. I'm going to talk specifically about heap leaching as an example, but the concepts that I'm going to talk about apply to other areas of the plant as well. So to talk about stockpiles, on the left of my screen is a typical model of a stockpile, a weighted average model. In a model such as this, all material information is averaged, and during planning and reclaiming, material variation cannot be distinguished. Other models currently in use include first in, first out, or last in, first out, but all of these models are quite simple, with the result being not having an understanding of material distribution and potentially unstable and unpredictable feed into the plant. A spatially aware model is far more representative of reality, and that's what we've developed and what you can see on the right of my screen. Using a model like this, you can manage both dumps and reclaims better. This model can be used to either plan and track blending within your stockpile, or strategically plan reclaims to suit your mine plan and achieve more stable results as the blend goes into your plant. To show you a real-life example of results achieved, on the screen is a mine plan versus plant actuals at a copper mine. The red and blue bars are percent difference and standard deviation of plan versus actuals over a 4-month period prior to the introduction of our spatial model, when a weighted average model was used. And then the green and yellow lines are after our spatial model was introduced, which we call grids, also over a 4-month period. All sample days or data points were taken from when there was over 60% plant feed from stockpiles. So these days we're heavily reliant on stockpile information accuracy. And as you can see, using the spatial model, they have been able to get much closer to their plan. So I've just jumped into Sequence Leapfrog. Now, as I said earlier, I was going to talk about integration. Our application is agnostic to systems and can use data from various sources, typically FMS if it's available, mind block models, topographical scans, and SCADA systems. We're also using machine learning and AI to improve anomalous data. Outputs are also integratable with other applications, and our 3D block model can be opened up into any geological modeling or planning visualization tool. And as I mentioned, I've actually got one of our models open now within Sequence Leapfrog. So this is a copper stockpile I'm displaying. And at the moment, I've got total copper on display. So you can see the spatial distribution of the copper. Now, I can change this to any other material property that I'm tracking. And I can track whatever material properties that I have information on. So for example, I've just changed to arsenic, and I can also see the spatial distribution of arsenic within the model. Another thing I can see within the model is how long the material has been sitting on the stockpile. So as you can see, this stockpile was created from the southeast and then went northwest. And this shows me the age in weeks of the material. And this is can be particularly important for any types of material where oxidation is important, for example, in a coal mine. Now, the model behaves realistically. It's not simply discrete blocks. Within the model, the material blends and moves, it flows downhill just as it would in real life. If there are dozers on the stockpile, either trying to blend or simply manage the stockpile, the material movement and blending is also taken into account. And ultimately, information is retained. You are no longer diluting information you had from your in situ model. And as I said, from here, you can start making decisions on the information that you have. So now I've jumped into the Brains app, which is our platform where I'm displaying a lot more information about the stockpiles. So I've got open a material reclaimed screen about the stockpile Calypso. And on this screen, you can see a lot of information about the material that has been reclaimed from this stockpile. If I show you this this graph, you can see you can see how the model has spatial understanding. So instead of being a flat line of your reclaims from a stockpile, you can now see that the material information that I've got displayed, and I've got total copper, recovery, and concentrate displaying on my screen, how they vary depending on exactly where the material was reclaimed from and the material properties at that location within the stockpile. Traditionally, in a weighted average model, it would look more like this red line. It might be just completely flat or maybe slightly sloping. And the difference between the red line and the blue line, and the blue line representing what's actually happening within the stockpile, is the difference between what you think you're getting with a weighted average model and what you're actually getting. So in this example, we've got 2.05% copper is what you would think you'd be getting, whereas you might actually be getting 2.2% or 1.85%. And so with this, you're not only not reaching your feed plan, but if you've got levers to pull in your plant for recovery or throughput, like additive in your concentrator, you are not only you're also not optimizing your output, and there's opportunity cost there. So it's not only about reclaiming from your stockpile, but there's also the opportunity to manage the build of your stockpiles and actively manage them in real time. So I want to show you a couple of interesting cases that we've seen. In the first one, there was over 100,000 tonnes of waste unknowingly dumped onto a stockpile when some road widening activity was being carried out. This was clearly seen in the 3D block model, as represented by the blue area in the model and the alerts in the application as shown on the bottom in the as shown as out of range dumps. So this means it was out of range for what was expected for that stockpile. If this had entered the plant, the opportunity cost of not processing ore instead of waste was over $5 million US. So instead, the material was isolated from the stockpile. In the next example, 20,000 tonnes of ore was used to create a platform in a pit, again unknowingly. The material was labelled to go to a stockpile, which you can see within the red boundary on the screen, but was actually dumped in a pit, and they found out was used to build a platform. The data quality screen that you can see on the bottom right was able to highlight the anomaly, and a plan was put in place to reclaim the material once the platform was no longer required. And this ore was valued over US 1 million. So to continue talking about stockpiles, now once the material comes from a stockpile and goes to the plant, what you can see on my screen at the moment is the combination of various different sources. So in the green here, I've got 52% of material is coming from my pit, going into my plant, and the remainder, 48%, is coming from 3 different stockpiles. And you can see in this graph the combination of all those different material sources and the ultimate material properties entering the plant over time. I've got the average over that time down the bottom in these text boxes. I have 11 days filtered, but you might want to filter for a few hours, for 6 hours, for a shift, for a day, so you can see exactly what is coming into the plant in real time. So it hit your crusher, and then that will be, then the people in the plant will have an understanding about what is coming in very soon into their plant. So this gives them more information about what is entering the plant than what was just in the mine plan. So this will allow decisions to be made to optimize recovery or plant output. So generally, the various solution panels available, such as the 2 that I've shown you, are useful by geologists and grade controllers for reconciliation, by mine planners to check compliance to plan, and the plant team to understand what material is entering the plant. So if we take this and move to the plant now, as I mentioned, I'm going to talk about heap leaching, but the concepts of what I'm talking about can be applied to other areas of the plant. I'm going to talk about 2 challenges within heap leaching and how material tracking can improve the outcomes. The first challenge is the presence of high fine material causing poor leaching kinetics and excessive consumption of acetylcyanide. Secondly, the presence of moisture in the tailing causes the material to behave with greater fluidity, which can prevent the construction of a stable heap, reduce the rate a rotary shovel can reclaim, and result in increased storage requirements and thus required environmental permits. We use machine learning to model the influence of the different material properties on process performance metrics, giving the marginal contribution of each factor to every prediction made. And this is what we call the material influence model, and the screen that I have open. So by knowing the planned and actual material input to your plant, you can predict the fine fraction and residual moisture. So on my screen here, these limits here in red are what we want to stay under. And this is our prediction of fine fraction. So you can see we want to keep the green and blue lines underneath this red line. And the same can be said for this residual moisture prediction. So we want to keep our residual moisture underneath this red line. Now, how do we do that? So we can look at the material influence. So once we know when the fine fraction or residuals might likely to exceed the limit, this is where we go. For the fines, some of the influencing factors are linked to the material properties and some are linked to the crushing circuit. And it is a similar story for residual moisture. Adjustments can then be made when high fines or high moisture is predicted. This can be adjustments around the crusher, blending ore, or adjustments to your agglomeration variables such as adding more binder. For moisture content, blending is also a possibility, or adding salt. And down here I can see the opportunity cost if action is not taken. So for this particular time frame that I have filtered, which is a month, which I can see up here, if I don't take actions when the predictions are above this red line, then there's an opportunity cost of over $100,000. So this is just one example in the plant of how effective material tracking can not only stabilize your product, but also increase the value of production. And as you can probably imagine from what you've seen, end-to-end material tracking helps break down silos between disciplines and data and facilitate constructive conversations between teams. And that is all from me today. Again, my name is Susan Kennedy from IntelliSense.io. I hope you found that interesting and useful.